Hi everyone, welcome back to the course on measurement and instrumentation, and this is our 8th week of discussion, and today is the first lecture of our 8th week. We are discussing the third module of the course, which discusses the transducer part of the course, and in the transducer we were basically discussing the temperature transducers in our 7th week, and we will continue our discussion on temperature sensor in this week also. Today we are going to discuss a new class of devices which are known as thermistors, which is very popular in temperature detection across the industry. We will also try to at least we will try to discuss in brief about the PN junction type of temperature transducers, which are also very popular in microelectronics applications. Okay. So, let us discuss the first topic, that is regarding the thermistors. Okay. We have already discussed the RTD in the previous lecture, in the previous week. Okay. So, let us talk about the thermistors today. Okay. So, a thermistor is a temperature sensitive resistor whose resistance changes significantly with the temperature. Okay. And this is widely used across the temperature measuring. This is widely used in the temperature measurement across industry, as I have mentioned earlier also, and we will see that what are the actual applications where you have to use thermistors, and for what kind of application the RTD that we have discussed earlier are more useful, and then we will also talk about other kind of devices for the temperature measurement. Again, it all depends on the end user, what is the application for which the end user is looking for a temperature detector. Okay. So, if you see this term thermistor, it is made up of two terms, one is thermal and second is the resistor, and exactly this is the definition that we have seen. Okay. So, the name is usually applied to mostly metal oxide based devices fabricated in different forms, including form of droplet that you can see on this slide also. These are droplet based metal oxide thermistors. We have these devices in the form of bars, in the form of cylinders, rectangular flakes, as well as they are available as thick films. Okay. So, if you see these metal oxides, they are mostly semiconducting in nature, starting from some narrow band gap to even wide band gap. Okay. So, there is a huge class of metal oxides that are available, and thermistors for the fabrication of thermistor we select categorically some of the semiconductors, and we will see what are the important parameter that we keep in our mind while selecting particular metal oxide for the thermistor applications. Okay. So, thermistor belongs to class of absolute temperature sensor, that is it can measure temperature which is reference to certain absolute temperature scale. Okay. So, the working principle of thermistor is based on variation of electrical resistance with temperature due to change in the charge carrier concentration, and this is exactly what we have seen in its name also, like it is composed of two terms, one is thermal and another is resistor. So, the working principle is exactly as its name conveyed, which is that it is based on the variation of electrical resistance of the device with temperature due to change in the semiconductor parameters, particularly the charge carrier concentration, and the resistance is basically is a function of temperature. Okay. There are two type of thermistors based on its operation. Okay. We have NTC thermistor, which is negative temperature coefficient thermistors. We also have PTC thermistors, which are positive temperature coefficient thermistors, and this is a typical resistance versus temperature curve for NTC and PTC thermistors. You can see that both are actually highly nonlinear in nature, while in PTC you are seeing that there is a temperature for which there is a sharp change in the resistance. We will discuss what this temperature is all about and what it signifies. Okay. So, let us see first the NTC thermistors, then we will see the PTC thermistors also. So, as the name suggests, negative temperature coefficient based devices. So, NTC thermistor, in the NTC thermistors resistance decreases as the temperature increase. So, most commonly used type of device is NTC thermistors, and in the device the dR by dt is basically less than 0. which signifies of course the decrement in the resistance with rise in the temperature. Okay. And their characteristics are they are very sensitive. Of course, they are highly non-linear in nature, but they have very fast response, and materials used are mostly the metal oxides based on manganese, nickel, cobalt, copper and iron. Okay. The PTC thermistors have just opposite behavior as compared to the NTC thermistors, and the resistance of PTC thermistor increases when you increase the temperature, means that your dR by dt component is greater than 0 or it is positive. Okay. And the characteristic of PTC thermistor, although name resembles, is totally different. Okay. Or the behavior is totally different as compared to the NTC thermistors. Okay. And you will find that there is a sharp rise in the resistance near the Curie temperature of the device, and this is what exactly is shown on the curve. Okay. And since there is a sharp rise in the resistance, these devices are mainly used for the protection applications. Okay. Protection from sudden rise in current. Okay. And material that is very popular for fabricating PTC thermistor is barium titanate in different form, maybe in the form of bar, in the form of thin film and so on. Okay. So, barium titanate BaTiO3 is very popular for fabricating the PTC thermistors. Okay. So, I have been using one word, that is Curie temperature, for this PTC thermistor, as I have mentioned that at Curie temperature there is a sudden rise in the resistance of the device. Okay. So, I hope that you are aware about Curie temperature. If you are not, let me just refresh the concept of Curie temperature so that we both are at the same page. Okay. So, Curie temperature you might have learnt in the context of magnetic material for sure. Okay. So, Curie temperature is the temperature at which a material loses its ordered internal structure and its property changes abruptly at this particular temperature. Okay. So, for magnetic materials like iron, below the Curie temperature, the atomic magnetic moments are aligned. Okay. And material behave as a ferromagnet below the Curie temperature, means that they possess a strongly magnetic characteristic, while above Curie temperature the thermal motion disrupts this alignment and materials becomes paramagnetic in nature, means that it is now weakly magnetic, which earlier it was strongly magnetic below the Curie temperature. Right. In the context of PTC thermistors, Curie temperature is the critical temperature at which the material in a PTC thermistor undergoes structural and electrical changes, which causes its resistance to increase very sharply, and that is what exactly we have seen earlier. So, it is mostly called the switching temperature of the thermistors, and that is why I have mentioned that this kind of thermistors are used for the switching applications. Okay. So, PTC thermistors are typically made up of barium titanate ceramics, and below the Curie temperature the material allows electrons to move relatively easier and the resistance remains low, while at Curie temperature the crystal structure changes from ferromagnetic to paraelectric state, which causes the grain boundaries to block electrons. And again, if you are not aware of grain boundary, I will suggest that you read about the defects in any crystal structure. Okay. So, we have different defects in case of any crystalline material. You have 0D defect, you have 1D defect, you have 2D defects, you have 3D defects and so on. 0D defect mostly cover the vacancy and other things. Okay. While the 1D defect mostly is known as the line defect. Okay. And sometime you have dislocations in this category, while the 2D defects have various defects including the stacking faults and the grain boundaries. Okay. So, grain boundary is, you can say, that kind of defect present in any crystal, and it is actually, as I have mentioned, it is a two-dimensional in nature, high energy interfaces in the polycrystalline materials which separate different grains of differing crystallographic orientation, and one of the example is shown here. You can see here that you have say this is I am calling this as grain 1 in a crystal. Okay. So, this is grain 1, this is grain 2, okay, and this is grain 3. All right. So, this is a polycrystalline material having different grains, and the grains have different orientations, and you can see that there is a boundaries between these grains. Okay, so this is the grain boundary that I was talking in the previous slide, that at the Curie temperature in this kind of PTC thermistors, the crystal structure changes from ferroelectric to paraelectric state, and this causes grain boundaries basically to block electrons. So earlier this was providing, the grain boundaries were providing very less resistance to the flow of electron, but now it is actually providing high resistance. So it is actually blocking the flow of electrons, say, from this grain to this grain. Okay, so at temperature below the Curie point, the grain boundaries actually is offering very little resistance or nearly no resistance, while it means that electron can cross these boundaries very easily and the current will flow normally. Okay, and in this state below the Curie temperature, the thermistor will behave like a low value resistor. Okay, now at Curie temperature, the material loses its ferroelectric order that I have just mentioned, and this will trigger the charge redistribution near the grain edges. Okay, and before Curie temperature, the boundaries were acting as a small speed breakers, while after Curie temperature actually they are behaving as a huge wall. So they are not allowing the electrons to flow beyond these walls. Okay, so this is because of course charge accumulate at the boundaries and create regions which actually repel the electrons at the grain boundaries. Okay, so above the Curie temperature, the potential barriers actually increases. So to cross a grain boundary, an electron needs energy, and this energy obstacle is called a potential barrier. I mean, you can understand this barrier very simple. You can connect it through the potential barrier that you have seen in the case of PN junction or any other junctions. Okay, so below Curie temperature, small barriers were there, means that the electrons were crossing easily, while above Curie temperature this barrier height you can understand is very high, and for electron it is now nearly impossible or very difficult to at least cross these straits. Okay, so electron now need much more energy to move beyond these grain boundaries, and since most do not have that enough energy, means that the movement drops sharply, and that's what is reflected in the form of sharp increase in the resistance. Okay, now the NTC devices, the NTC negative temperature coefficient of resistance of the NTC thermistors can be as large as several percentage per degree Celsius, which is very small. Okay, now this allows the thermistor circuits to detect very small changes in the temperature, and this is what actually differentiate it from RTD devices. Now this small percentage change per degree Celsius was not possible with RTD. Even we will learn about a new kind of temperature sensor in our second lecture of this 8th week, where we will talk about the thermocouples. Even this kind of small change that I am mentioning over here is even not possible with that kind of devices. Okay, so we'll see that what is the limits of thermocouple and all, but for RTD you are aware that what it can do, what materials these are made up of, and how it compares with NTC thermistors. And now it is even much clear that for what application NTC thermistors are used and for what applications you have to use for, or you have to look for RTD devices. Okay, now a conventional metal oxide thermistors has a NTC that I have mentioned, means that its resistance decreases with increase in temperature, and the NTC thermistors resistance as of any resistor is determined by its physical dimension and the material resistivity that we know R is equal to rho L by A. Okay, so when I say the NTC thermal resistance is determined by the materials resistivity, I am talking about this particular factor, and when I am saying that it is determined by the physical dimension, I am talking about this L by A. Okay, and the relationship between the resistance and temperature in this cases is highly non-linear and usually given by the beta equation, and the beta equation is something like this: RT, which is the resistance of the thermistor at temperature T, is equal to R naught, which is the resistance of thermometer at certain calibrating temperature, into e to the power beta 1 by T minus 1 by T naught, where T naught is the calibrating temperature and T is the actual thermistor temperature, and this beta is very important, and this is the materials characteristic. Please note that all temperature in this discussion is in Kelvin and even beta is in Kelvin, and commonly beta ranges between 2600 to 4200 Kelvin, and for a relatively narrow temperature range it can be considered temperature independent, which make it a reasonably good approximation, and that's why for NTC thermistor we will be using this beta equation regularly. Okay, RT is equal to R naught into e power beta into 1 by T minus 1 by T naught. Okay. Generally, this NTC thermistors can be classified in 3 major groups depending upon the method by which they are fabricated. Okay. And the first group which is very common is called the bead type. Okay. The bead may be bare or coated with certain materials like glass, like epoxies, or even they are encapsulated into a metal jacket. Okay. Now, all these beads have platinum alloy lead wires which are sintered into a ceramic body, and exactly we have seen this. So, you have this kind of lead, 2 leads say made up of platinum alloy. Okay. This alloy is used particularly for better strength and even to keep the cost in control. Okay. And you had metal oxide deposited somewhere here, and it is embedded in a epoxy or they are encapsulated into a metal jacket, right? And these are metal leads or metal alloy leads. Okay. So, then we have another type of thermistor which is a chip thermistors, and chip thermistors again have a surface contact for lead wires. They are usually, these chips are like rectangular chips, and they are formed by even simple methods like tape casting process. Of course, for the tape casting you have to go through several processes including screen printing, spraying, vacuum metallization of the surface electrode and so on. Okay. Now, the chips are either bladed or cut into the desired geometry. So, this rectangular shape is not only shape that these devices are available. You can have multiple type of devices, but again they all will be called as a chip thermistors, right? The third type of thermistor is fabricated by a deposition of semiconducting materials on suitable substrate such as glass, alumina, silicon and so on, and these depositions are mostly done by physical vapor deposition as well as the chemical vapor deposition. Metal oxides can be deposited by both the means. I have mentioned earlier also that you have 2 deposition techniques. You have physical vapor deposition techniques and another you have chemical vapor deposition techniques. Physical vapor deposition techniques require either evaporation. For metal oxides, E-beam, electron beam evaporation is preferred method. Okay. Then you have sputtering, where you have targets, okay, target of certain metal oxide, and you hit it with certain kind of ions, okay, or say particles, for example, let it be more generic, okay, and this high velocity particles will dislodge certain atoms or molecules in this case of metal oxide, okay, and it goes in a vacuum chamber, and it, when it sees a cooled surface, it goes and deposit say atom by atom. Okay. So, since this is done physically, you are actually physically hitting it and dislodging it, this process is known as PVD, while in CVD you had say quartz tube, inside you have maintained certain pressure, temperature and so on. This say temperature can be given by this say resistive heating or say inductive heating of the coil. You have this susceptor here, and on top you have certain wafer on which you want to deposit metal oxide, and you bring certain metal precursor. Say for example, if you want to deposit say copper oxide, okay, you bring certain precursor for copper, okay, and then you introduce oxygen or any other source for oxygen, and they react and they form copper oxide and they get deposited. So, here actually basic chemical reaction is happening, and that is what we call it CVD. Of course, PVD and CVD is a class of fabrication technologies, and you can study this more in certain fabrication courses, but this is how they are deposited. Okay. And These thermistors are very popular for integrated sensors and for specific class of thermal infrared detectors. Okay. So, they are more robust and kind of industry accepted. Okay. So, advantage of the thermistors overall is that they have high sensitivity and they can be fabricated in a very small size. Okay. They have a faster response time, low cost, and they can be fabricated with simple circuitry. Okay. However, they have various limitations also, as we have seen that both devices, be it NTC or be it PTC, both are highly nonlinear in characteristic and they have limited temperature range. Okay. Again, they have self heating errors associated with them and they will require frequent calibrations. Okay. The application is much beyond than temperature detection in general use. They are used at industry scale. Okay. They are used for the measurement in digital thermometers, medical thermometers, then the HVAC systems in houses or in industry. Okay. For control applications, they are used as in temperature controllers, incubators, ovens. Okay. For protection, PTC, as I have mentioned, are very popular because of their sharp increase in the resistance beyond the Curie temperature. Okay. Therefore, also used in the inrush current limiting and for the battery protections. Okay. So, these are actually general utilization of the thermistors, and for NTC and PTC we have different categories of applications. It is not that they are similar, and they compete with other industry scale temperature detectors very well. Okay. Particularly if the change that you want to measure is not very high, for those kind of application it's significant to become even higher. Okay. Although they are semiconductor based devices, but they are not very popular for chip applications, and there we have semiconductor PN junction based devices, whereas semiconductor PN junction in either a diode or in a BJT exhibit a quite strong thermal dependence. Okay. So, if the forward bias junction is connected to a constant current generators, the resulting voltage becomes a measure of the junction temperature, and that is how a semiconductor PN junction becomes a temperature detector. Okay. And a very attractive feature of this kind of devices, it's a high degree of linearity, as you can see for silicon based devices. Okay. Of course, if you see the slope is around minus 2.3 millivolt per degree Celsius for silicon at 10 micro amp, and for 1 microamp it is minus 2 millivolt per degree Celsius. Okay. The current to voltage equation, we know that for a PN junction diode can be simply written as I equal to I naught e power QV by NKT minus 1. This is a popular diode equation. Okay. We know. Okay. Say I am calling it equation 1. All right. Now, it can be shown that the temperature dependent voltage across the junction can be expressed by this particular equation. I am calling this equation 2, which is V is equal to Eg by Q minus 2 KT by Q into ln capital K minus ln I. So, please note that we are using two K's. One K is this small k, which is the Boltzmann constant, and I have another K, this is a constant which is basically a temperature independent quantity. Okay. In this equation, this Eg is the energy band gap for silicon at absolute 0, Q is the charge on an electron. Okay. So, this can be derived from this equation and another equation of say I naught, which shows that I naught is directly proportional to the concentration of intrinsic concentration and so on. Okay. So, we are not going in more detail, but you can derive this equation from the previous equation as V equal to Eg by Q minus 2 KT by Q into ln K minus ln I. Okay. So, this is a temperature dependent voltage across the junction. Okay. So, it follows from this equation that when the junction is operated under constant current conditions, the voltage linearity relates to the temperature, and the slope can be given as B equal to dV by dt, which is equal to 2K by Q into ln K minus ln I. All right. So, 2K by Q into ln K minus ln I is the slope. All right. And usually for silicon junction operating at say 10 milliamp, which is of course kept constant, the slope, which is, if you remember from the first module, the slope for this kind of linear device is nothing but its sensitivity is approximately around 2.3 millivolt per degree Celsius that we have just seen. However, it decreases by 0.3 millivolt per second per degree Celsius, and it becomes 2 millivolt per degree Celsius for 1 milliamp constant current source. Okay. So, this is in general about the PN junction as a temperature sensors. Okay. So, PN junction devices are very popular where you want to use it for on chip applications. They can be fabricated directly on silicon and they occupy extremely small area. So, with your process, basically the linear process by which you are fabricating your device, you can also fabricate your temperature sensor. Okay. And they provide you real time junction temperature, and no other sensor integrates this easily inside a chip. Even for integrating the thermistors, you will require a very high temperature for the deposition of them. Okay. So, the temperature may not be CMOS compatible, but this kind of device can be easily integrated. Okay. So, this is briefly about the thermistors, which is again a kind of semiconductor device. Okay. And the other one that we have just seen is a PN junction, which is purely a semiconducting device and can be fabricated by CMOS technology. Okay. And can be integrated with for the on chip applications. One more temperature sensor that has come in this class is the thermocouple. Okay. And in the next class, we will continue our discussion on temperature sensor, and we will learn this third or fourth category of temperature sensor, where you will see that we will have two different metals and they are joined together. Okay. So, two different materials, say material A and B, will be joined together, and one junction will be kept at, say, at higher temperature, and when you keep the other junction temperature at lower temperature, and because of this temperature gradient, there will be a current flowing and of course a voltage dropped. Okay. So, this is known as Seebeck effect, and this we will discuss in our second lecture of our 8th week. Thank you.